Last time we cracked open the engine, loss, gradients, backprop. We watched a network drive its training loss down, step by step, until it nearly hit zero. Felt like a win. But here's the uncomfortable question this episode is about: down on what data? Because a model can ace every example it studied and still flunk the real exam. We're in the evaluate stage of the pipeline now, the honesty stage, where we find out if it actually learned or just memorized. Think back to that falling loss curve. The callback printed a beautiful number every epoch, but that number was measured on the exact same examples the model was training on. Of course, it goes down. The model is allowed to peek at the answer key. A low training loss tells you almost nothing on its own. The data the loss is measured on is the whole story. Here's the trap: a network with enough capacity won't learn the pattern, it'll memorize the examples. Every quirk, every noisy data point baked in. It's the student who memorized last year's exam word for word, then sees this year's paper and freezes. Perfect on what it saw, useless on what it didn't. That's overfitting. And it has a signature, a shape you can spot in 2 seconds. You split your data and plot two curves. Training loss keeps sliding down, but validation loss on data the model never trained on, bottoms out, then turns and climbs. Train falling while val rises. That crossing point is overfitting drawn in ink. So you need an honest mirror. That's the validation split. A slice of data you hold back from training and check after every epoch. It's your early warning system. And the iron rule: your test set is separate again, locked in a drawer, opened exactly once at the very end. Tune on validation, never ever peak with test. The moment you do, it stops being honest. Now the fixes: first, dropout. During training, you randomly switch off a fraction of neurons each step, say 30%, gone, every batch a different 30%. Sounds destructive, it's brilliant. The network can't lean on any single neuron, so it's forced to spread the knowledge around to build redundancy. Robust beats memorized. Second, early stopping. Remember that val loss curve turning upward? Early stopping just watches it and says, the moment you stop improving for a few epochs, quit and roll back to the best weights you had. No babysitting, no guessing the epoch count. It finds the sweet spot for you and restores it. And when you finally test, don't settle for a single accuracy number. A confusion matrix shows you which classes get mixed up. Maybe 92% overall, but it's quietly confusing class 1 for class 2 more than anything else. The matrix puts that failure off the diagonal where you can't miss it. Score tells you how much, the matrix tells you where. Wrap all of it into one idea. Regularization punishes complexity and rewards generalization. Dropout, an L2 weight penalty, batch norm, early stopping. Different tools, one philosophy: make the easy path the general path. A model that generalizes has earned the right to ship. But first, it needs eyes. Next time, we teach a machine to see. Let's read the code. One script, 2 pages. Page 1 builds and overfits a small net on purpose, then plots the damage. Page 2 adds every regularizer we just talked about, refits with callbacks, and scores it honestly with a confusion matrix. Watch the val curve change shape between the two. Imports and data, Keras, NumPy, Matplotlib. We make a small, slightly noisy 3-class blob dataset, small on purpose because small data overfits fast and shows the gap clearly. Then the critical move, a 3-way split, train, validation, test, 3 buckets, 3 jobs, no overlap. The overfit model, a deliberately oversized dense net, 2 wide hidden layers, no regularization at all, compiled with Adam and sparse categorical cross entropy. We fit it for 200 epochs with validation data, so Keras logs val loss every epoch. This one is built to memorize. the diagnosis plot. We pull history and draw train loss against val loss. This is the left panel, train sliding to the floor, val bottoming out around epoch 23 and climbing after. That gap is overfitting you can point at. The regularized model, same shape, but now every layer carries kernel regularizer LL2, followed by batch normalization and dropout 0.3. The L2 penalty keeps weights small, batch norm stabilizes, dropout forces redundancy, 3 defenses stacked. The callbacks, early stopping watches val loss with patience 10 and restore best weights true. Model checkpoint saves the best model to disk as we go. We refit and this time fit stops itself early. Watch the terminal, it prints epoch 33 early stopping, then the line that matters, restoring model weights from the end of the best epoch. 23, the honest score. We evaluate on the test set opened for the first time, then run predictions through tf.math.confusion matrix. No scikit-learn, pure TensorFlow. We plot it as a heat map and the before-after loss curves side by side. That's evaluation done properly. Trust the validation mirror, regularize to generalize, judge on test exactly once. This model has earned the right to ship, but everything today was numbers in a table. Next time, the data is pixels. We teach a machine to see with convolutions and settle cats versus dogs